Okay, so in this video, we will prove the factor theorem. If you remember, this theorem says that a polynomial f of x has as a factor x minus a if and only if f of a is equal to 0. Before we prove this though, let's review a few basic notions about polynomials and long division. The first concept is the degree of a polynomial. And we usually denote the degree of a polynomial simply by deg. So if we had, say, f of x as our polynomial, then we'd write degree deg of f of x. And all the degree is the largest power of x that shows up in the expression. Let's look at a few examples. If f of x, our polynomial, was equal to 5x to the 4 minus x cubed plus 3x minus 8, then the degree of f of x is equal to 4, as 4 is the largest power of x that shows up in the expression. And that's it. That's the degree of a polynomial. If our polynomial was x to the 9 minus 6x squared plus 7, then the degree of our polynomial now is equal to 9. Let's look at just two more examples. If f of x was, say, x minus 4, then now the largest power of x that shows up is 1, because x is x to the 1, and so f of x has degree equal to 1. And you may ask, what if f of x is a polynomial that is actually a constant? What if f of x equals 2? Then in this case, what is the degree of this polynomial? And here, if you think about it, there is no power of x. But if you think of the constant 2 being 2 times x to the 0, as x to the 0 is equal to 1, then the degree of the polynomial is equal to 0. So if you have a linear polynomial, so some multiple of x plus some constant, the degree is 1. And if you have a polynomial whose degree is 0, then it must be a constant polynomial, and vice versa. If you have a constant polynomial, there is no power of x that shows up on the surface, but it really is x to the 0, and so the degree of a constant polynomial is equal to 0. Now let's see how the idea of the degree of a polynomial fits with long division. Let's remember what is the statement of long division, and then we'll consider two examples. So what does long division say? Well, you start with two polynomials. Say here f of x and g of x, where g of x is not a zero polynomial, and you divide f by g. So if you apply long division, and you said, okay, we'll divide f of x by g of x, then you would get the following result. So f of x will be equal to g of x times some other polynomial q of x, called the quotient, plus also possibly a remainder polynomial r of x. But r and q must satisfy, r and g must satisfy a very important condition, that being that the degree of r must be strictly less than the degree of g, your divisor. And that is what long division is. Divide f of x by g of x, and you can write f of x as g of x times q of x. Now g of x is your divisor, q of x is the quotient. R of x, if there is called a remainder. the leftover of the division. And the remainder satisfies one key property: its degree is strictly smaller than the degree of your divisor g. So let's see how this plays out in two examples. The first one is a warm-up. The second one will be for us the crucial example that will lead us to a general result, and with this we'll be able to prove the factor theorem very easily. So here's our first example. We will take f of x to be the following cubic polynomial. So 2x cubed plus x squared minus 5x plus 1. And we will take g of x, our divisor, to be a quadratic polynomial. So x squared plus 4x plus 3. So notice here that the degree of g of x is equal to 2, as 2 is the largest power of x that shows up in the polynomial. And now we will divide f of x by g of x using long division. I'll write this first long division using the French way of writing it down, and in our second example I'll write it using the English notation. So we divide 2x cubed plus x squared minus 5x plus 1 divided by g, which is x squared, plus 4x plus 3. If you use the English notation, of course, you simply interchange your polynomial f of x and the divisor g, and you do the same thing. So we ask what times x squared gives us 2x cubed, and of course remember that it is important when you do a long division that you write your polynomial from the largest power of x decreasing to the smallest power of x. So 3, 2, 1, 0, 2, 1, 0. What times x squared is 2x cubed? 2x. We multiply our divisor by 2x, so we get 2x cubed, 8x squared, plus 6x, and we subtract. 2x cubed minus itself is 0. X squared minus 8x squared, negative 7x squared. Negative 5x, negative 6x, negative 11x. 1 minus 0, plus 1. And now we ask, are we done? Well, at this stage of our long division, this is our remainder, sorry, the remainder, and this is the quotient. But the degree of the remainder is 2, and the degree of our divisor is 2. So we are not done long division. We are only done once the degree of our remainder is strictly smaller than the degree of our divisor. So we have to keep going. As 2 is not less than 2, we repeat. So plus what times x squared is negative 7x squared? Well, this is negative 7. Multiply by negative 7, you get negative 7x squared, negative 28x, negative 21, we subtract. Negative 7x squared minus itself cancels. Negative 11x negative negative is positive 28x, but 28 minus 11 is 17x. 1 minus negative 21 plus 21, so plus 22. And now you ask, well, are we done? Well, the degree of this polynomial is 1. The degree of our divisor is 2. 1 is strictly less than 2, and so here we are done with our long division. This is our quotient, q of x, and this is our remainder, r of x. And so now we can write our conclusion from this long division. Our polynomial f of x, 2x cubed, plus x squared minus 5x plus 1 will be the divisor, x squared plus 4x plus 3, times the quotient, 2x minus 7, plus the remainder, which is 17x plus 22. And that's what long division gives you. So you divide f by g, and you end up with f is g times some polynomial plus the remainder, and the remainder has a degree of 1, which is less than the degree of the divisor, which was 2. Alright, so this was our warm-up example. Now let's do a second example, which for us will be our key example, using the same polynomial f of x, but I will change our divisor for a simpler linear polynomial. And this simple example will lead us to a key observation when dividing a polynomial by a linear polynomial. So f of x, the same cubic polynomial, 2x cubed plus x squared minus 5x plus 1. And now we take as our divisor g a degree 1 polynomial, simply x minus 2. So, as we've just said, the degree now of g of x is equal to 1, as the largest power of x that shows up in the polynomial is x, which is x to the 1. So when we divide f of x by g of x, the remainder will have to be of degree strictly smaller than 1, but that can only be 0, and as we'll see, the remainder will be a degree 0 polynomial, therefore a constant. Let's perform this long division, and I will write the long division using the English notation. So in French we would write f g. In English then we'll write g and then f. So we have 2x cubed plus x squared minus 5x plus 1. And we're dividing this by g of x, which here is x minus 2. And now we do the same thing, except we will now write here our quotient, and what will come out of this end will be our remainder. So what times x is 2x cubed? Well, 2x squared. Multiply by 2x squared. And we get 2x cubed minus 4x squared. We subtract 2x cubed minus itself. This cancels. X squared minus negative 4 is plus 4x squared, so 5x squared. Negative 5x minus 0, negative 5x. 1 minus 0, plus 1. Well, are we done? This is now our remainder. The degree is 2. Our divisor, as we have said, has degree 1. Well, 2 is bigger than 1, so we have to keep going. So we repeat. What times x is 5x squared? Well, that's positive 5x. Multiply out. We get 5x squared minus 10x. We subtract. 5x squared minus itself is 0. Negative 5x, negative 10x is positive 10x. 10x minus 5x is 5x. 1 minus 0 plus 1. Well, the degree here is 1. Our divisor has degree 1. 1 is not smaller than 1, so we have to keep going. Plus, what times x is 5x? Well, clearly plus 5. Multiply by 5, you get 5x minus 10, subtract. 5x minus 5x is 0. 1 negative negative 10 is plus 10, which is plus 11. Now we have here a constant term. So the degree of this polynomial is 0, and 0 is less than 1, and so the degree of our remainder is strictly smaller than the degree of our divisor, which indicates that our long division is over. So this is our q of x, our quotient. Oh, sorry. This was our divisor. This is our g of x. This is our quotient. And this is now our remainder, which is a constant polynomial, as we have said, because we divided f of x by a linear polynomial of degree 1. The remainder must be of degree less than 1, which can only be 0. Therefore, the remainder must be a degree 0 polynomial, which is a constant polynomial. Let's write our conclusion and then make a simple observation. So, f of x must be g of x, our divisor x minus 2, times the quotient 2x squared plus 5x plus 5 plus the remainder, which is simply 11. It's a constant remainder. Now let's ask quite simply, what is f of 2? We divided f of x by x minus 2. Let's ask what is f of 2, but first not using the result of long division, looking back at the original polynomial. So f of x, if you go back to the original polynomial, is 2x cubed plus x squared minus 5x plus 1. So now we will ignore what we've just done with long division and simply evaluate f at 2 directly. So you'll have 2 cubed, which is 8, times 2, which is 16, plus 2 squared, which is 4, minus 5 times 2, which is 10, plus 1 plus 1, 16 plus 4, 20, minus 10, 10, 10 plus 1, 11. And if you ask, well, does that look familiar? Hopefully it does, as it was our remainder. And you might ask, well, is this a coincidence? And the answer is no. Let's now look back at the result of long division, and let's plug in, instead of x, 2, and see that we get the remainder. As, once we replace in our divisor x minus 2, x by 2, this will simply be 0. Plug in 2 in here. 2 times 2, 4. Times 2, 8. 8 plus 10, 18, plus 5, 23. Plus 11. But as you can see, the value of the quotient at 2, this is q of 2, is irrelevant. Because no matter what the quotient is equal to when x is 2, our divisor will be 2 minus 2, which is equal to 0. And so 0 times anything is 0, and we're left with the remainder. And this is the key observation that will lead us to a very simple proof of the factor theorem. Now you may ask, well, is this a coincidence? And the answer is no, right? So if you divide a polynomial f of x by x minus 8, as your divisor has degree 1, the remainder must have degree 0, and we'll prove right now that the value of this constant must be equal to simply the value of the function at 8. So let's prove this very easily. If we have a polynomial f of x, and we divide this by x minus 8, where a is a constant term, then what will we get? If you look up, well, we'll have the divisor times the quotient, the quotient of some other polynomial, say q of x, plus our remainder. And you ask, well, what do we know about this remainder? We are dividing by a linear polynomial, so degree 1 polynomial. The remainder must have degree strictly smaller than 1, so it must be of degree 0. But a degree 0 polynomial is a constant, so plus some constant. This must be a remainder as I've just said, we are dividing by a degree 1 polynomial. The remainder must have degree strictly less than 1, so it must be 0. And if you have a 0 degree polynomial, it can only be a constant. And now let's prove that the constant is equal to f of a. Well, this is true for every x. Let's replace x by a. So we'll get f of a is equal to a minus a times q of a plus c. No matter what x is, c is always c as it is a constant. And if you notice, we don't know what the value of q of a is, but it doesn't matter. This could be any real number. It's being multiplied by a minus a, which is 0. Anything times 0 will be 0. And we're therefore left with simply c. And you can see, as we have claimed, c is the value of the polynomial at a. And so now we have our conclusion. F of x, if we divide by x minus a, will be equal to x minus a times some other polynomial plus a constant remainder, and this constant remainder must be the value of the polynomial at a. And with this observation, we can now easily prove the factor theorem. So if you divide f of x by x minus a, where a is a constant, the result will be f of x equals x minus a times the quotient plus a constant remainder, which has to be equal to f of a. Alright, so now let's prove the factor theorem using this simple observation. And of course, first we'll remind ourselves, what is the factor theorem? It's also sometimes called the zero theorem. Here the assumption is f of x is a polynomial. So we're going to say that x minus a, where a is some real number, is a factor of our polynomial f of x, if and only if you remember, this double-headed arrow means if and only if f of a is equal to 0. And you can see why it's called the factor or the zero theorem, as one statement says x minus a is a factor of f of x. The other statement says a is a zero of the polynomial, as f of a is equal to 0. Now what is, again, this logical symbol? As we have just said, it means if and only if, which stands for a logical equivalence, which means both statements look different on the surface, right? Here we're saying x minus a is a factor of our polynomial. Here we are saying that a is a zero of our polynomial, f of a is equal to 0. On the surface, it looks like both statements are saying something different. What we're going to show, this is what this means, is they are logically equivalent. So if you have one, you have the other. So if this statement is true, automatically this one must be true as well, and vice versa. Hence the double-headed arrow. If this statement is true, then automatically this statement is true as well. And the idea of why this is useful, again, is sometimes we look for a factor of a polynomial, but it's easier to look for a value of x that makes the equation 0. So once you have a 0, if f of a is 0, you have as a free factor x minus a, minus your 0. So let's prove this. We have to prove both directions, so that if this statement is true, then this one is true. And then we have to prove that the converse is also true. If this statement is true, then so is this one. we'll start with the easier direction. So we assume this will be true, and we'll prove that this is also true. So we assume that x minus a is a factor of f of x. That is our assumption. X minus a is a factor of f of x. Our goal is to prove that because of this, f of a must be equal to 0. Well, this will be the easy direction. If x minus a is a factor of f of x, what does that mean? Well, f of x is equal to x minus a times some other polynomial. That's what being a factor of f of x is, right? F of x is x minus a times some other polynomial. Well then, if this is true, what is f of a? F of a is a minus a times q of a. But regardless of what the value of q is at a minus a is equal to 0, and the result is 0, which proves that f of a must be equal to 0. And now we're done. We have just shown that if x minus a is a factor of f of x, automatically f of a must be 0. Check. Let's prove now the other direction. Now we will be assuming that f of a is 0, and we'll prove that x minus a is a factor of f of x. That is our only assumption. F of a is 0, and our only goal is to prove that because of this assumption, that this is true, to prove that x minus a is a factor of f of x. Now this is not so obvious, but with our preliminary work, this actually will be fairly straightforward if you recall what we have just proved as a result of long division. So we have proved just before with long division, if you have a polynomial f of x, and you divide this polynomial by x minus a, you have f of x will be x minus a times the quotient, polynomial q of x, plus the remainder. If you remember, our divisor has degree 1, so the remainder had to have degree 0, and the only polynomials with degree 0 are constant polynomials. And our conclusion was that this is not just any constant, it is quite simply f at a. And this is the result of long division. And now we're basically done, right? So by long division, f of x is x minus a times some polynomial plus f at a. But since our assumption was that f of a was equal to 0, then all we're left is that f of x is x minus a times q of x plus 0, so it's just x minus a times q of x. But then if f of x is x minus a times some other polynomial, clearly x minus a is a factor of f of x, and this completes the proof. We've proved that if f of a is 0, automatically x minus a is a factor of f of x, which was our conclusion. If f of a is 0, prove that x minus a is a factor of f of x. And that's it. And this is how you prove the factor theorem using the result of long division. So always remember, the use of this theorem is for us, we'll be looking for a way to factor the polynomial f of x. And on the surface, it may be quite difficult to find a factor simply by inspection, but it will very often be easier by inspection to locate a 0 of the polynomial, and once you have a 0, x minus this value will be your free factor. And that's it.